that
Okay.
if we, let's see if I can do this first. No, it looks like that's where it's gonna be. Okay. All right, you're welcome to use the computer if you're more comfortable with that,
Okay.
if you want to be able to see it this way. I'm sorry I can't get it up on that monitor there, but
Oh, right.
but I think you should be familiar with your presentation by now.
Yeah, right.
Great, all right. And once it's over, I'll come down, I'll come back in here, so if you see me sitting there, just,
Okay.
I'm not trying to tell you to
Oh,
do
okay.
everything.
Okay.
The only thing to be aware of is it's supposed to go until 1:30.
Okay.
Sometimes it goes over, as long as you're truly done by 1:45, yeah, 1:45,
Okay.
because there's a class that starts at 2.
Oh,
And I
okay.
need some time to download
knock
everything.
out.
So that would be great.
Yeah, I'll try to knock things out by 1:30.
Okay, that sounds good. All right, well, Ed should be down here in just a minute,
Okay.
and I think you should be all set.
All right,
All
great.
right, thanks so
All
much.
right,
Good
thank you
luck.
very much. I
Yeah,
appreciate it.
you're welcome. Just don't forget to turn on your microphone.
Okay.
just getting here, but I've
Oh,
got,
yeah. Oh, that's all right.
I'll probably introduce you,
Okay. No,
have a cheat sheet,
all right, very nice.
but I'll wait probably
And 2-3 minutes.
3 or 4 more minutes. All right. Kids are getting big. We're great. We're great. So I assume I want to go to lunch when we get.
Yeah.
And then there was one faculty member in EE that was interested in talking to you after that.
Okay.
I don't know if he can be here for the talk or go to lunch with us, but.
Yeah, that'd be great.
Do we have a role? Is that what this is? I don't know.
Oh, okay. No, I didn't realize that.
No, that's my usual. They get credit for
Okay.
going to a certain number of centers.
No, right.
Yeah. Is this your main work right now?
Yeah. This is what we've done.
That's what Micross does.
Well, Micross, not really. That's what I did at RTI. Micross came up and bought the group, and they kind of took me with them because they liked that I helped them money. So
Okay.
they did more like a die manufacturing. They do a lot of like wafer pumping.
But you're still doing what you were doing at RTI.
Yeah, I'm still doing the thermoelectric.
Oh, okay.
So I'm still.
I guess you're gonna tell us all.
Yeah. It's just they want me to do because this is Micross is sort of like a manufacturer. They supply parts to DoD, whatever they need, whatever die, whatever they need. But they want to get into research. That's their plan. They think there's research dollars to be had. So I guess they think I'm a guy who gets out for them.
Sure. Well,
I'll give it a shot.
probably a good strategy.
Well, let's see. Actually, to be honest, I want to get together the whole group. Actually, I have 3 happiness to say.
All right. Professor job?
Yeah.
All right.
Professor, and they have that internet there, fabrication facility, and they want to have some professor come in and run that. So talk to some folks there, and they told me I could do it.
You would be in which department?
You see.
All right. Exciting.
We'll see how it works out with my process. All right. Anyway, this is what I do now. I'm kind of getting. If I get back, I used to say I might plan to try to get back into the track. I was at our staff here.
Yeah, we'll talk about the Micross at lunch. I'm a lot of stuff involving around here with me. So, we have that reactor over there. I've got a student working on it.
Oh, okay.
Haven't get any money. Haven't been able to get any funding. So, can't keep it going forever.
Yeah.
I might be reaching the end of the road on that. One of these months or years. Well, I'm to the point where if nobody's interested in it, 59 years old, I'll just teach and do some other things on it, which we'll talk about all that. And we're doing some other interesting stuff, kind of getting into audio and acoustics, some area of personal interest, and there's money out there for acoustics. Materials. So. Yeah, sure, we do that all we can. I'll wait maybe 1 more minute. Well, we'd like to have a little more than that, getting into senior design time.
We should do it off. Yeah, because then everybody.
Standard deviation would be the
We should do that. We should have like everyone not.
They're always interested if you have to.
What would that be?
Jobs and they talk about that.
Okay.
Your company's hiring.
Not necessarily just a loan.
No, yeah.
Like so, when I talk a little bit about Micross,
Yeah.
we have recently.
yeah, I don't think anybody else even knows the same. No, that well, no, a lot of people age and that. I didn't know what he was.
There was a couple of these because it was like
Well,
a bell curve around 40 and then like a.
Yeah, I had 40.
Okay, well, worked for a startup here for what,
Right.
6 months or a year,
Yeah.
back about 10 years ago. And so he was on campus for a while. And then when he left here, he went to the Research Triangle Institute, which I don't know if you're going to tell us a little bit about RTI and what RTI is.
Yeah, we get into that.
And then technology was sold or
So yeah,
to Micross.
Micross company we're talking about here. Right.
So he's now with a company called Micross in the Research Triangle. And of course, there are a lot of high-tech jobs in the Research Triangle, Raleigh, Durham, Jacksonville area. So PhD from NC State.
Correct.
In
2006.
Three nitride semiconductors in 2006. And so if you have everything you need, you got everything.
I think I do.
Liquor-wise, and no further ado.
All right, great. Thank you. All right, thank you, Professor. I appreciate the invite out here, and thanks for everybody for coming out. As Professor Stokes said, my name is Phil Barletta. I work for a company called Micross, AIT. AIT stands for Advanced Interconnect Technologies out in Research Triangle Park. I've been there since October. The decade before that, I was at RTI International. I don't know if any of y'all are familiar with RTI. It's a nonprofit research institute started back in the 50s in the Research Triangle region. Basically what happened is we had the three schools, NC State, UNC, Duke, in that region. A lot of students were going there for their educations and then spreading out elsewhere. And the NC legislators said, well, we're attracting all these great students, we're educating here, but then they're fanning out to other parts of the world. What's one thing we could do to keep them here? And one of the things they did was started Research Triangle Park to try to get a core of companies there to keep the talent, stop the brain drain, as they called it. And the cornerstone of that was RTI, the nonprofit research institute, which I worked for 10 years. However, recently at RTI, our group was purchased by Micross. They saw the sort of things that we did there. They liked our wafer fabrication. We do work with 3D integration, with wafer bumping, myself with Thermoelectrics. They liked all the things that we did, so Micross came and bought us from RTI, and that's my organization now. I'll talk a little bit about Micross, give you a sort of introduction of what kind of things they do and how they, where their strengths are, that sort of thing. And then we'll jump right back into the technical aspect. We'll talk about thermoelectrics, basically the two sort of independent effects that combine to form the thermoelectric effect and some of the ways that thermoelectric materials are judged. We'll talk a little bit more about, I've come from a material science background, so I like the materials aspect of it. We'll talk about that a little bit. And then we'll jump into applications. There's two primary applications for thermoelectric materials and devices. One is probably going to be a little bit more interested to folks in this room, and that is power generation. The second is also for thermal management of devices. And again, we'll cover all this stuff in great detail as we move on. First, as I said, I'll talk a little bit about Micross. Micross is a company based down in Orlando. They liked the work that we were doing at RTI, and they went ahead and they bought our group out. And Micross is basically delivers, it's basically a die manufacturer, delivers any kind of die that the government needs. They work for defense industry, for space, you see medical, industrial. And what they want to do now is they've never done research before, they're more of a manufacturer, but they want to get into research, and that's where RTI came in. That's what they liked about our group. That's what they liked about the kind of thing that we did. And they said, okay, we want to do look at your 3 silicon via stuff. We want to do your thermoelectric stuff. We want you to be a part of us. So that's what happened. As I said, our particular group at Micross is called Micross Advanced Interconnect Technology. That's where the AIT comes from. We just recently got ISO 9001 certification. That was a big deal for us. We're also ITAR registered, which is also a big deal, because back at RTI we were very big into defense contracting. A lot of DARPA work. My career I've done mostly DARPA work, so that's very important for the kind of things that I do. We do a little bit of a mix at Micross of more sort of like customer-based service work, and that is, here's a lot of wafers, we want solder bumps on a lot of them, versus the more researchy kind of thing, which is sort of the wing that I am, sort of the side that I am. I do the more sort of high-risk, high-reward, low TRL level type research. And in particular, with the things that I work on, the research I work on, are thermoelectric materials and devices. Do we have familiarity with thermoelectrics in this room? Anyone? A little bit we see. That's good. But so anyway, I'm going to jump into it for the folks who aren't quite as familiar. We could talk a little bit about what thermoelectric means, what the phrase means. It's actually the combination sort of two things. You have the Peltier effect, which basically is using electrical power to generate a temperature difference between two sides of a material. Peltier discovered this in France. As he was working on it, we also had a Johann Seebeck in Germany discovering that you could actually use a delta T to generate power in a device. So here we have one scientist working on generating a delta T using power, and another scientist actually generating power by using a delta T. And you essentially had both sides of the same coin. Both Peltier and Seebeck essentially discovered the same sort of physical phenomenon, which we call now the thermoelectric effect. Now, of course, as with any material, or any phenomenon, I should say, different materials are better at it than others. So what we do to judge whether or not a material is going to be a good thermoelectric material, whether it's going to be able to generate a delta T based on a current or a power based on a delta T, is using the figure of merit ZT. ZT has three primary components. The first is the Seebeck coefficient, which is the alpha you see here. And of course, that's pretty intuitive. It's just the amount of voltage per unit temperature difference that you get in your material. Next thing is the electrical conductivity. You want to have, as you see it's in the numerator, you want to have a high thermal conductivity in your material, or sorry, a high electrical conductivity in your material. And that's basically just because you don't want to have much. You want to minimize the I squared R heating that you have in your material. Your I squared R heating in your thermoelectric material is just a parasitic, and you want to go ahead and get rid of that. The last major component is, of course, the thermal conductivity. What you want to have here is you want to have a low thermal conductivity, because if you're trying to generate a delta T, a temperature difference from one side of the material to the other, what you don't want to have is that heat transfer back up from one side to the other. Now, knowing what all these components mean and looking at them right here, you automatically see a problem. One thing jumps out at you right away. That is, you want to have a high electrical conductivity but a low thermal conductivity. That doesn't happen in nature. And that's one of the challenges we have as material scientists working with thermoelectric materials, is this type of material just doesn't generally exist. So being able to, first of all, identify materials that kind of fit into this realm is a challenge. And also basically doing things, once you have the type of material, the sort of alterations you can make to the material structure, to the processing to make it increase its or keep stable its electrical conductivity, but drop its thermal conductivity is challenging. One of the ways in which it's done is kind of a secret is in this last line here. When you have a thermal conductivity, you have both a lattice thermal conductivity and an electrical thermal conductivity. If you drop your lattice thermal conductivity, you will drop your electrical conductivity as well. So what people tend to do is work with the lattice thermal conductivity. And when I talk about some of the materials, we'll get into a little bit more detail on how that's going to be done. A few more quick things with the ZT. A lot of folks talk about, if you read thermoelectric literature, talk about the power factor. The power factor is basically just your numerator here, your Seebeck squared and your conductivity. And just to give sort of a frame of reference as we talk about some of these numbers more, something around 0.75, maybe to 1 is the type of ZT that you're going to want to have in your thermoelectric material if it's going to be any good, if it's going to have a lot of usefulness sort of in the real world. For the material, like I said, finding materials is a challenge. What type of materials can you use that are going to give you not only the Seebeck, but also give you the high electrical conductivity and also the low thermal conductivity? Basically metal tellurides. Bismuth telluride, lead telluride, germanium telluride. They're the type of materials that are generally used for thermoelectrics. Most popular, the most common way you're going to find with thermoelectrics. That's because they have small band gaps. Their band gaps are generally less than 1. They're more semi-metal than they are semiconductors, so that's going to give you your low electrical conductivity, and the high electrical conductivity. And the thermal conductivities are typically very low because you have big atoms. They're down at the bottom of the periodic table. Those big atoms vibrate very, very, very slowly, and so essentially you have a relatively low thermal conductivity. The most common of these metal tellurides in general use is bismuth telluride. Basically because most applications we're concerned with are going to be around room temperature, and bismuth telluride operates the best at room temperature. As you can see, compared to some other materials here, right around 300K, you're going to get the best performance out of bismuth telluride. So if you go and you buy a thermoelectric module from a Melcor, from Marlowe, Custom Thermoelectric or something, it's going to be bismuth telluride, and it's going to be sort of a bulk, several millimeter thick elements of NMP type bismuth telluride. The type of performance you're going to get out of a commercial bismuth telluride module like that is going to be delta T, meaning the maximum temperature difference you will get from a single stage device is going to be around 70 Kelvin. And the amount of heat you're going to be able to pump with that is 10 watts per centimeter squared at a delta T of 0. Don't get too concerned about this right now. I'm going to talk in a little bit more detail about what these numbers mean and why they're important, but I just want to introduce sort of the frame of reference as we go forward into thermal management, the type of numbers that are available commercially. Other common thermoelectric materials in addition to the tellurides are scutterdites. Scutterdites are basically like a complex metal arsenide or metal antimonide structure, which essentially has what's called a rattler atom. Essentially, it's a hollow structure that has some type of large, usually a rare earth atom inside of it. That rare earth atom is going to rattle, it's going to shake around in that lattice at a different frequency than the actual structure of the material itself. And that sort of disconnect, that sort of disharmony, manages to scatter the thermal conductivity, which means you have the lower thermal conductivity you need to have a good thermoelectric effect. Scutterdites are very popular with NASA. NASA uses these in their MMRTGs. They're basically multi-emission radioisotope thermal generator. And essentially what that is if you consider a radioisotope giving off a constant supply of heat. If you put this constant supply of heat with a thermoelectric material will convert that heat into electricity, and you have a constant source of electricity. And so that it's very reliable. There's no moving parts. There's nothing that can really break per se. So NASA likes to take this type of radioisotope generator, put it in their satellites that go unmanned into space. Clathrates are another type of material you may hear when you read about thermoelectrics. It's essentially like a cage type structure. And again, it uses the same sort of rattler atom that we talked about with the scutterdites. And essentially the two different sort of resonant frequencies of the materials causes a drop in thermal conductivity, which again gives you the high ZT. Another interesting group is the PDOT PSS group of materials. I'm not a polymer chemist, so I can't tell you too much about these or their crystal structure, but I know that they're a polymer. And anytime you have a polymer that could do something, for example, in this case, thermoelectric effect, it's pretty exciting because they're very, very low cost, easy to manufacture, cheap, lightweight. These type of materials aren't really performing a whole lot right now, but I mean it's an exciting potential. If we could get some sort of way to get the PDOT to work properly, we could really really push the thermoelectric manufacturing forward. Lastly, another group that I'm particularly interested in is the silicides. Magnesium silicide, manganese silicide, manganese tin silicide is another one. And basically what you'd have is you have a thermoelectric material. Some of these ZTs have been reported to be about 1, as I said, is a pretty good type number. And what's nice about these is they're a low-cost, non-toxic, earth-abundant material. One of the problems you have when you're dealing with a lead telluride, with a bismuth telluride, antimony telluride, you're dealing with materials that are expensive, which are toxic, and frankly, there's not a lot of them in the earth. Essentially, for example, bismuth telluride, we quite literally don't have enough tellurium atoms in the world to do all the things we want to with bismuth telluride. For example, there's some companies that are looking at putting bismuth telluride in every car for seat warmers, for pulling heat from the exhaust and putting that back into electricity. The problem is the tellurium is just not there, and that's a problem which is really you really can't solve no matter how good of a scientist you are. Which is why the magnesium silicide type materials are getting a lot of traction, a lot of interest right now. So we talked a little bit about the materials. Now let's go into a little bit into nitty-gritty of how thermoelectric materials work. What's this sort of mechanical behavior that we're seeing here? Essentially what you have is a thermoelectric device right here, a nice picture from Wikipedia, where we have an N-type material and a P-type material. You have a heat source up here, and you have your bottom side sunk to a heat sink. So essentially what you have here, you have a hot side here, you have a cold side, heat sunk, you have a very low thermal conductivity material here, so you've generated at this point a delta T. If you have a good thermoelectric material, we know a couple things. We know that we're not going to get heat transfer from the hot side to the cold side very efficiently because we have a low thermal conductivity. We also know that we're going to be able to move the electrons and holes, the charge carriers, pretty effectively because we're going to have a high electrical conductivity. And also with our high Seebeck effect, we know that we're going to be able to generate a voltage. So when we have this delta T generated and our charge carriers move from the hot side to the cold side from the thermoelectric effect, you essentially can create a circuit where you have charge carriers moving and you have power. The amount of power that you get is going to be dependent on the delta T. ZT is important, as I talked about, but even more important is delta T. The more temperature difference you can generate from the hot side to the cold side, the more carriers that are going to be moving from the hot side to the cold side. The more carriers you have, the more current you have, the more power that you have. Another sort of neat thing about thermoelectrics is that they can be cascaded. You could essentially have one on top of the other. So basically, if you have a certain temperature range up here, maybe you have something 300 and it drops to 150. Underneath, you could have something, say, 150 that drops to room temperature. And that's sort of one of the tricks that we did in our work at RTI. Here's a sort of a real-world example of a two-stage thermoelectric generator. We have one stage here, one here. And we've measured efficiencies as high as 21%. And when you think about the amount of heat that's out there, just the amount of waste heat that's being, wasted in the world today, to be able to get 21% of that back into usable electrical power is a pretty exciting opportunity. Here's another example. This was some of the highest power we have gotten from a device from my time at RTI. As you can see here, here's our P and N-type couples right here, a 4x4 centimeter piece. And we've had an output power of this of 56 watts at an efficiency of close to 10%. You had to bring the hot side up to 800 degrees C to get this type of performance. But if we do have an area where we have sort of high-grade waste heat, 800 degrees C hot side, you could get some pretty significant wattage at some decent efficiencies out of it. Now, we talked a little bit about the efficiency, about the high delta T, and I really sort of want to stress this because if there's one thing that you take from this talk about using thermoelectrics for power generation, I think this is it right here, and that is delta T is extremely important, particularly if you're dealing. A lot of folks say, they'll come to me and they say, well, hey, I want to have I have a 100 degrees C hot side. Can you give me a thermoelectric that's going to give me a lot of power? And I'll say, well, not really. And they say, well, what if you increase the ZT? And again, I say, well, when you're dealing with low delta T's, you could have great ZTs, but if your delta T is too low, you're really not going to get the type of performance that you need. It's not until you get out into the hundreds of degrees that we're really seeing the type of efficiencies that are important, that are sort of exciting in this field. So remember that the most important thing when you have for a thermoelectric device is you want to have the high delta T. That's going to give you the most sort of bang for your buck from an efficiency point of view. One of the ways in which thermoelectrics are one of the areas in which people are looking at them is for heat recovery for heat recovery in gasoline engines. Only about 25% of the energy that you burn with your internal combustion engine actually goes into pushing the car ahead and your devices in your car. About 40% of it, as you can see here, is just kind of wasted. And can we grab some of that 40% of your wasted heat and put it into and put that to good use? Some other areas where people have looked at is in power plants. Excuse me. A lot of waste heat being generated at power plants. Can we use thermoelectric generators to go ahead and bring that electricity back? Geothermal vents is another sort of an interesting area where you have, just like naturally occurring in the earth, where you have sort of like hot spots, hot areas. Can we sort of take waste heat from that, generate electricity from there? And a lot of folks, specifically some folks at NC State, are looking at the human body. It's a very, very low delta T that you get from your body compared to the outside, compared to the ambient. But that's sort of a source of power that we all have just on us. Can we somehow use that power to power our devices, our watches, our heart monitors, that sort of thing? Some of the things that went on at RTI, my colleague David Stokes did a lot of work in this area, was looking into using thermoelectrics for sort of like humanitarian means. RTI was very big on improving the human condition. This is a sort of research that they liked quite a bit, and frankly quite a lot of us did as well. This is a biomass cook stove, and what these are is in the third world, in Africa, Kenya, Tanzania, some of the poor places in India. This is sort of the main source of heating and cooking for a lot of the people there. And basically they find whatever they could find out, whether it be pieces of wood or anything that will burn. They'll go ahead and feed it into their cook stove, and they'll burn it, and they'll use it to heat their homes. They'll use it to cook their food. The problem with this type of cook stove, especially when they're being used indoors inside their huts, is they're not very clean. There's a lot of particles that come out. There's a lot of carbon monoxide that comes out. So there's sort of like a global health crisis of people using this type of cook stove inside and developing respiratory problems over their life. There's a pretty simple solution to this problem, and that is to feed more air into the cook stove. The more air, the more oxygen that gets into the cook stove, the cleaner the burn, the less particulates you have, the less carbon monoxide you have, the less breathing problems that the indigenous people have later on in their lives. The problem is, how do you actually get power to them to put a fan on this? It's as simple as putting a fan on this cook stove. But when you're in poor regions of India, when you're in Africa, how do you get the power to power these fans to make these burn cleaner? Well, the answer is in thermoelectrics. You have a cook stove, it's burning hot. By putting a thermoelectric device on the stove itself, you're using that heat to generate the power to run the fan. The fan blows extra air into the burn, and you have a cleaner burn, and you have better lives for people. Another sort of humanitarian aspect of the work we've done at RTI has been this is an interesting project that was funded by Bill Gates, the Gates Foundation. Another problem in the third world is basically sanitation. Basically, you have people, dumping their waste into rivers that downstream people are using that water to bathe. They're using that water to cook. So the problem of what to do with human waste in poor, very, very heavily populated areas is a big problem, and one that Bill Gates himself, wanted to look into and has funded RTI as well as some other groups to look into. So what RTI has done is they've developed basically a toilet, a standalone toilet, that basically the waste materials go into, are inserted here. The liquid and solid waste are separated, and the solid waste is actually dried and burned here, while the liquid waste is disinfected down here. The power to this system comes from thermoelectrics, because actually in human solid waste there is a ton of stored power there. So that human waste is burned, creates heat. That heat is actually converted into electricity via thermoelectrics. It runs the whole system. So those are both the cook stove and the Gates toilet are two examples of places where thermoelectrics could be used to put towards literally the greater good of humanity. Very proud to have worked on these projects. I'm going to talk a little bit more about some of the things I'm working on now, which is using thermoelectrics not just for power generation, but this is for thermal management. Thermal management is a big problem because if you have an electronic device, you're putting current through it. If you're putting current through it, you're going to have I²R problems, and that's just a simple fact of life. You can't get away from the fact that whatever electronics you're going to use are going to have these I²R issues. And electronics don't like to be heated up. They're going to have lifetime issues. They're going to have efficiency issues. Quantum cascade lasers is something I'll talk about a little later on. That's an area that I'm looking at now. Servers and data centers is a new thing. As cloud computing gets more and more popular, you pack more and more servers into more and more places running higher and higher. They're just going to get hotter and hotter. And a lot of military. For example, some military aircrafts, their FADEX, automated digital control, fully automated digital engine control, basically drones, are those electronics get hot as well. So what can you do to stop this heating of electronics? Thermoelectrics is one application that could be used. Specifically, the work I did at RTI and which I'm carrying now as Micross deals with thin film thermoelectrics. I talked to you a little bit earlier about the sort of bulk thermoelectrics that you would buy from Custom Thermoelectric or Marlow or Melcor, where you have sort of thick millimeter size active layers of thermoelectric materials. What I have here with my materials is I actually grow something more like 5 to 7 to 10 microns of materials. My P-type is a bismuth telluride, antimony telluride superlattice, essentially a multi-layer structure. And I have a delta-doped N-type that sort of behaves similar to like a 2D electron gas, where I have high mobilities and high electrical conductivities. So what we do is we actually go, this probably looks familiar as we talked about the thermoelectric device structure earlier. But instead of having a bulk P and N-type, as you see, I have a small, just thin active area. So we have a test vehicle. What we have here, we have a die here that's 1.2 by 1.2 millimeters. These are our leads here. And this is where I pump my heat and generate my power right here. And here's an array, for example, of what we can build at RTI or Micross. This is deliverable for the DARPA ACM program. We actually delivered this 1.2 by 1.2 millimeter module that pumps 100 watts of heat. Size of a penny, pumps 100 watts of heat. Pretty amazing little guy. So we'll talk a little bit. I talked to you about thermoelectrics before, these bulk thermoelectrics. I'm talking to you here about thin films. Well, what advantage do thin films have? What do thin film thermoelectrics do that bulk can't? Or what can they do better than bulk thin films? The first is, of course, form factor. If you have something that's thinner, it can fit into places that thicker guys cannot. Here's an example of a two-stage thin film thermoelectric device versus a two-stage bulk thermoelectric device. I personally haven't found an application yet where I need this, but I kind of keep it in my back pocket for now because I think just simply speaking, just the size is an advantage. The second is speed. We think about the very, very high thermal resistance of thermoelectric materials, and you think about trying to pump heat through a thick millimeter scale versus a thin micron scale thin. Well, the heat is going to go through the thin material much, much more quicker, much, much more efficiently than it's going to go through the bulk. And you can kind of see here when we talk about a bulk, here's your elements here. That's the size of the high thermal resistance material here, whereas it's just a little guy up here in the thin film module. And this photo you have here is from an experiment I did. This is back in one of my DARPA projects. And essentially what I did was take two modules, a thin film thermoelectric, which I built, and the bulk thermoelectric module, put a drop of water on each one, and then basically turned on the power. What we essentially saw was that the thin film thermoelectric module froze that drop of water in about 15 seconds. The bulk thermoelectric module froze it in about 48 seconds. So just the speed at which the heat can be pulled away is a big asset compared to what you would get in a bulk module. The other thing that's neat about thermoelectric modules is the reversibility. We'll take a look here at this ACM module, the one I pointed out earlier today. And I could show that with this guy, with these IR camera images, they could go from hot to cold essentially instantaneously. Now, obviously, making something hotter is not a big deal. You could just do that with a filament or whatever. But being to have a device that you could just by switching the polarity, either have it become a heater or a cooler, it's kind of cool. You can do that with a bulk thermoelectrics as well, but because you have that thick thermal mass of the thermoelectric material, it's a very, very slow process. Thin film thermoelectric does it almost instantaneously. Now, number four, the fourth advantage is sort of the biggie. It's sort of what I've sort of based my recent publications on and what we've based some of our recent projects on, and that is with heat pumping. The heat pumping equation is given right here, and heat pumping is just telling you how much heat can you move from one side of a material to another. And this is not talking about conduction. We're not talking about you have something at, say, for example, 50 degrees, and you have something else at 20 degrees, and the heat going that way. That's conduction. A block of copper could do that. We're talking about constant temperature on one side to the other, bringing heat over a constant temperature, a delta T of 0. Or in some cases, you'll get into actually pulling heat against a temperature gradient. For example, you could have your device to be cooled at, say, 10 degrees C. You could have your heat sink at 30 degrees C and still pull heat from the 10 degrees C to the 30 degrees C. That's sort of the magic of what thermoelectric materials can do. So as we talk about this, you can look at this expression here. And of course, we have the Seebeck. We know what the Seebeck coefficient is. We can talk about that up here. We have our conductivities, or resistivities. We know we want our electrical resistivities to be low. We want our Seebecks to be high. The temperature of the cold side, of course, the temperature is going to have an effect. F is a packing fraction, of course, that you want to have them more densely packed if you're talking about Q max per area. But the last guy here, the thickness of the thermoelectric elements. That's really the secret. As we were looking at these equations, we said, hey, wait a second. People are really looking at, increasing Seebeck, increasing or decreasing your resistivity, decreasing thermal conductance. But what about this guy here? What can we do about the thickness? And by basically, it's just a one-to-one. As you drop your thickness down, you're going to increase your Q max. So therefore, if we have what we normally work with here, which is the 5 to 20 micron thick TE elements, you should be able to get significantly better heat pumping than we get from the bulk guys, which are for sale now. We have the materials to do it. We have the build the devices. Let's go ahead and see what we get. So that's what we did. We started with our 20 micron material. At the time, that was sort of our hero material, the best stuff we could do. And we actually started measuring the heat pump. We modeled and we measured it. And as you see, we're getting things like, we talked about before, you get something along the lines of 10 for the commercial modules. And we're getting numbers like 40, 70, 90. That's pretty good. These results are pretty encouraging. We're getting something that's exciting. We had some problems with these modules here because they had a larger area, and so we lost, even though we had a lot of heat pumping, a lot of heat coming through them, the pumping per area wasn't as good. And so you could see, we're getting numbers which are, around 100 watts per centimeter squared. Like, wow, that's 10 times better than what the bulk guys do. But, we grow 20 micron material. Can we drop down? Can we grow lower? Can we grow maybe 8 micron material? So that's what we did. We brought the thickness down to 8 microns. We fixed our die dimensions at 600 micron by 600 microns, so we wouldn't have this problem with the drop in Q over A. And we looked at different types of geometries of contacts. We looked at basically having 2 round contacts on each N and P type. And we also looked at having these, instead of being round, be squares. But the big thing was to maximize packing fraction. We took a look at this guy right here, and I said, well, let's make our contacts as large as possible on the die. That's going to maximize our packing fraction. You can remember the F over L. And also with it being 8 microns here, that's going to minimize the thickness there. Could we actually get better than this 90-100 watt per centimeter squared? And the answer is, we did. We got a lot better. We got over 250 watts per centimeter squared. Now again, the ones people are buying off the shelves, again, are 10. Laird, one of the companies that spun out from our RTI group, they make thin film thermoelectrics too, but even with those, they only get something like 70, 80 watts per centimeter squared. So these results were just crazy. 250 watts per centimeter squared was sort of a world record. We even also were able to demonstrate 180 watts per centimeter squared at a delta T of 10. And again, let me remind you, that means we had something, the object we were cooling was actually 10 degrees cooler than the heat sink. So even though we were working against a 10-degree temperature differential, we're actually able to move 180 watts per centimeter squared. So how does that compare to other devices? Well, you can kind of see here. This is essentially a load line. People use this a lot in thermoelectrics to kind of describe your performance. Your bulk thermoelectric cooler is going to be a guy right here. You're going to get a good, we talked around 70 delta T, and that's a nice number, but the heat pumping isn't there. The commercially available thin film, again, you're looking at something like 80 watts per centimeter squared. But our guy is this guy right here. And you can see that load line is way further to the right than anything that anyone else has described before. So what we can do better than anyone else in the world at RTI and now at Micross is to build devices that can have a high heat pumping at a low delta T. We published this in Nature Communications about 2 years ago. It's out now with more details of the work. And actually what we did is we pitched this to DARPA, and we were able to get a 3-year, $2.7 million DARPA award based on these results. Of course, when we told DARPA about this, the first thing that they said was, how do we know you're doing it right? How do we know that your test measurements are what they need to be? And so we talked to some folks at the University of Maryland, Professor Bao Yang and Professor Avi Bar-Cohen, who was the DARPA program manager at the time, and said, okay, we saw the results that you guys got. Let's see if we get the same thing. And what was nice about this is it's not only a different lab testing our devices, but it's also a different testing setup right here. Whereas we use what's called a Q-meter, which is essentially just a metal block with thermocouples up and down to measure the heat that goes through the device. We use a laser at University of Maryland. And whereas we use thermocouples to measure temperatures on the hot and cold side, University of Maryland uses an IR camera. So basically what it is, I took my devices up to University of Maryland. We tested them there. And we found that their results actually were a little bit better than ours. They took a look at the delta T max, which was the maximum amount of temperature difference between the two, where we measured 36.1. Maryland measured 37. And for the, this wasn't our 250, this is one of our lower ones, our 214. Maryland actually measured that to be 234 during their setup. So this made me really happy. This is almost like sort of an old school scientific setup. You measure your results in your lab, you build your devices, you measure results, you get what you get. You go somewhere else and verify. And it worked out really well for us. So basically, like I said, what we went is we talked to DARPA, and we said this is the, they came out with a BAA for a program called the Matrix, Materials for Transduction. And I said, okay, based on what we've done here, we have an idea. First, we think that based on the numbers we have so far, that we could build a thermoelectric device that's going to pump 500 watts per centimeter squared with a delta T of 15 and COP of 1. COP means coefficient of performance. It's essentially the amount of heat pumping you get divided by the amount of energy you have to put into the device to make it work. So that's good. That's going to be it's going to be a tricky metric, but that's what we said. And so we said that basically we want to actually integrate our thermoelectric devices with a QCL, with a quantum confined laser. Quantum confined laser is basically the perfect example of the type of electronic device that doesn't need to be cooled to a low temperature, but just needs to have its heat pulled away. They generate a lot of heat, a lot of current going through these QCLs. You've got to be able to pull that heat away. This thermoelectric device can do it. We also work with a company up in Pennsylvania called Thermocore that actually develops a heat exchanger that can be useful for us. And what we want to be able to do is be able to enable, with our thermoelectric device, a quantum cascaded laser that can output 20 watts of optical power. And why is 20 watts of optical power, why is this important? Why is this an interest of the Department of Defense? Well, these QCL arrays can be used for it's called IRCM, infrared countermeasure, against man-portable defense systems, these man-pads. What man-pads are is essentially shoulder-fired rockets. They're heat-seeking. So if you have, whether it be a military helicopter or even a civilian jet during takeoff and landing, these man-pads can be used to take down these planes, take down these aircrafts. Basically, the problem sort of started back when Muammar Gaddafi was in charge of Libya, because apparently he loved these things. He loved these shoulder-fired rockets, so he just stockpiled them in his arsenal. And then when his regime fell, they just sort of disappeared into the Middle East. So now they're being sold on the black market, and a lot of groups, including Islamic State, are trying to use these man-pads to shoot down military helicopters. And it's really only a matter of time before they get the idea to use them against civilian aircraft. What's nice about QCLs is QCLs can put out, as you see here, they can put out, if they have sufficient power, put out a pulse that basically throws the heat-seeking missile off track. It just sort of confuses it. But essentially you need to have, you can't do this with 1 or 2 watts or 5 watts. You need to have something long, you need to have 15, 20, 30 watts to do that. But the problem with that is that the thermal management just isn't there for these QCLs. There's just really nothing that can cool these QCL arrays enough that you could get this type of power out of them consistently. And so that's where our technology comes in. We're in the middle of this DARPA project now. We've made some good progress. We'll talk about that. So a little more to go. We haven't worked a lot on the integration yet so far, but that's one of the sort of more exciting things we're working on. Another thing that we're working on now is trying to, we recently have a patent on the what I call the high-tech design, highly integrated thermoelectric cooler. Basically, what I mean by that is if you look at a thermoelectric device, we've seen this sort of what we call the Stonehenge structure a lot this afternoon. But essentially, you have an active layer here, you have an active layer here, and you have a lot of sort of like structural components here. And that's just sort of over time, if we've developed these thermoelectric devices, we've had these layers in there. The problem is, from a thermal standpoint, these are nothing but parasitics. These just get in the way. These just degrade the performance. And as you can see, all these layers, all we need is this and this from a thermal point of view to make it work. But we have all this other nonsense. So the question is there a way to sort of cut down on these layers and integrate these directly into the components that need to be cooled and directly into the heatsink? So that's what we have here. Again, well, if we grow our thermoelectric material directly on wafer, process them on wafer, and then actually use, instead of putting them on a separate header that will be then integrated into thermally attached to the heatsink, let's integrate the devices onto the heatsink themselves right here, and actually integrate your part that's being cooled. Let's integrate that directly onto the thermoelectrics as well, so you don't have, all these sort of structural headers to hold everything together. Let the heatsink and let the device you're cooling hold everything together. So this is a tricky sort of integration problem, but something we're working on now. Again, presented at iTherm. We also have a patent on this as well, patent application. Another problem here, one of the things I wanted to talk about as we sort of wind up the technical part of the talk here, one of the big problems, big challenges with working with bismuth telluride, we talked about the low conductivity, we talked about the low band gap, and what that means is that the contact resistivity of these materials has to be very, very, very low. Something like in nitrides, it's, what is it, 10 to the third is a good contact resistivity, Ed? Maybe 10 to the fourth? When you're talking about thermoelectric devices, we're talking about 10 to the minus 8 ohm centimeters is the kind that we need. We're at about 10 to the minus 6 right now to get the 250 watts per centimeter squared. But in order for our modeling to make our devices work to improve, you need to get down into the e to the minus 8, you even need to the minus 9 type range. Fortunately, we have been able to demonstrate that on sort of test structures. We use a TLM transmission line technique to go ahead and put a series of sputtered metal contacts onto the, we normally would use electroplated or evaporated contacts. In this case, we developed a technique to put sputtered contacts down. And again, we're seeing the type of contact resistivities that we need to get the results. We've actually worked a lot with quite a bit with Sandia, who's another performer on the DARPA Matrix program, in order to get this to work. And we've actually just finished up a manuscript and submitted to Advanced Materials. That's all I have from a technical point of talk. Again, my name is Dr. Phil Barletta. Please, if you want to talk to me any further, any questions, please let me know. Always available for collaborations or just further discussions.
All right. Do you have any questions?
Yes, sir.
Can you go back to your device structure?
This one?
So the bottom part is conductive, the T.
Right, the T is an aluminum nitride bottom header, and so it is thermally conductive, but it's not electrically conductive. The electrically conductive part is this trace here, the S, and so your electrical path is through here, up here, out, down, and out. But basically, essentially, that's the way your electricity is going to travel. Thermally, everything's traveling this way.
Okay.
But essentially, the problem we have with this is anytime you have any sort of mass, you're going to get a delta T across that mass, and you don't want delta T's across anything besides your thermoelectric. Yeah.
Are people using those superlattices, those 3-5 superlattices?
Yes.
With the Indian muscle like getting a tin line?
Yes.
For this type of application?
It's funny. I actually did a little bit of work on that, and I wonder if you saw my paper. I submitted at MRS a while back based on that, and perhaps at higher temperatures they may perform a little bit better, but generally the band gap is just a little bit too high to get good thermoelectric behavior out of them. I did, like I said, I don't remember the results. I did write a paper on that for MRS a while back, and the results were okay, but we were talking about, I think, ZTs of like 0.2, 0.3. So it was interesting, but nothing, not in the sort of the 0.8, 0.9, 1 range that we need to be really useful.
The band gap of that material system can be obviously really small.
Yeah, if with the type 2 behavior, you can bring it down. I think you could. I don't know what the thermal conductivities or what kind of seebeck you would get out of it. It's potentially possible, yes.
Just for in general, when you have two types of materials making superlattices,
Right.
even say gallium arsenide, aluminum arsenide, the phonon modes are very different between the two materials.
Right, and you get scattering at the interfaces.
You can reduce the thermal conductivity. If you can keep the electrical conductivity, that would be good for you.
Okay, yeah, yeah.
People trying, say, even for the test of principle,
Let's talk afterwards about this. I think, because like I said, I did some preliminary work on it, but it never really got too far. But let's compare notes afterwards. I think that'd be good.
I think we're scheduled to talk to you a little later on, right?
Yes.
Oh, great.
Okay, so yeah.
Okay.
Good. Yep.
All right. In the range of 10 to the 20, 10 to the 19, 10 to the 20.
So those p-type, n-type, your goal is to have the low conductivity, right?
Yes, we want to have high electrical conductivity, low thermal conductivity. The problem, of course, is that when you have, Wiedemann-Franz law basically relates the electrical conductivity to the thermal conductivity. And if one goes up, the other goes up. If one goes down, the other goes down. But that only applies to the, if we go back here, that only applies to the electrical portion of the thermal conductivity. So the tricks that people sort of play to sort of get around the Wiedemann-Franz law, the restrictions of the Wiedemann-Franz law, is, probably should have went back to the computer for this, is to basically play around with the, thermal conductivity, or to play around with the lattice thermal conductivity, this guy right here. Because your electrical thermal conductivity is going to be directly related to your electrical conductivity itself by the Wiedemann-Franz law, but your lattice thermal conductivity is where you could play your games.
Also, did you try the spin-printed content for the TLM method?
No, we've done, like I said, we've typically done plating, electroplating, and evaporation. And for this project, we actually discovered a sputter method to do that. But no, we haven't done any sort of printing or anything.
But spin-printed is much more affordable, right?
I don't know. I'm not familiar with that method for electrical contacts and semiconductors in general. But
in the PV, we use the spin-printed contact all the time.
You use what? Oh, screen printed. Okay.
Yeah, because that's the most cheap and most.
Okay, and what type of metals do you use?
Silver.
Okay. Yeah. I'd like to talk to you about that afterwards as well. Let's look into that.
So I know process check. I know some of you have a somewhere else to be, maybe at 12:30. I just passed these sheets around so you can sign in, especially if you're a student and you're signing in for credit. So sorry to interrupt.
Oh, it's all right.
The coefficient of performance 1 sounds like a tough spec to me.
Yeah,
That's
yeah.
basically 100% efficient, as I
Not necessarily 100% efficient. It's just that if you put in, if you're pumping out a watt of heat, you have to put in a watt of electricity. They don't want a situation where you're pumping in, 3 watt, or you've had to put in 3 watts of electricity to only pump 1 watt.
Okay.
I mean,
so
that's
it's not really an
efficiency. It's just a division of 2. Like I said, I typically get like COPs of like 0.6, for example. So I mean, I'm putting in more electricity than I'm pumping out. But yeah, like a refrigerator, for example, like a refrigerator in your house, that's going to have a COP of like 3 or 4. Just because the Freon cycle is pretty efficient.
Any other questions?
Oh, yes.
Any mature technology people can now use in their car?
Well, yeah. There's a company that's looking into putting thermoelectrics in automotives. Like I said, the biggest problem they're up against, and I think I mentioned it here, is the tellurium issue. That's why they're looking into the silicides I talked about, either magnesium silicide or magnesium tin silicide, trying to get those, because they actually did the math and they said, hey, there is quite literally not enough tellurium that we have found on the Earth to make as much thermoelectric modules as our Vision in the car. So that's why they're actually working on some of these Earth-abundant materials, trying to get those to work out. Or if you get the polymers to work out, that's great. I think that's a tough haul. They're pretty far behind. But the magnesium silicides, actually, you're seeing ZTs, approaching round 1.
Polymer is probably going to melt.
Yeah, yeah. I mean, if it would have to be a low grade, maybe like a human body type thing. Like I know Darius Vashi at NC State is looking a lot into body heat harvesting, and he's looking at both like low power devices and actual like good ways to couple the thermoelectric device to your skin. And in a situation like that, because it's flexible, because it's cheap, because it's non toxic, I think that would be great for human body applications. But it's a tough application.
Any other questions? Let's thank our speaker one more time. Thank you.
Oh, hey.
Stan Thompson.
Hey, nice to see you.
Is anyone looking at using these in parallel with the hydrogen fuel cells to use the expansion of the hydrogen for the cool side and the waste heat from the reaction, and so just adding it to the
right. I haven't heard of that.
Well,
that's
consider
interesting.
it.
Yeah, that's
and,
good. All right.
I'm retired.
Okay, yeah.
But what I do.
Thank you.
From RTI to Micross. There's less of a month of cases, but I think once we sort of get our feet out from it a little bit, get our feet under us a little bit, we might be able to work with and stuff like that. So.
Okay, what did you talk about in the email?
Yeah, let me give you. Yeah. Well, you got my email address. Unfortunately, I realized that I do stuff. Yeah. Just say like employment opportunity at Micross.
Okay.
And let me see what your resume says, and run up the flagpole and see what we see what's available.
Okay. Thank you. Actually, I'm looking for a research management company.
Okay.
So it's interesting. It's my interest.
He changed the slide before I could copy down his contact information. Do you have it?
Heat exchanger, cooling system.
I can probably just roll.
I didn't get his name. That's the right spelling.
But that doesn't have contact information on it.
That's all right. I got the telephone
Oh,
number.
okay.
So I can probably work it. May I have this? This is yours.
You can. Yeah, sure. Yeah, you can.
Thank you.
Good. I'm Ed Stokes.
Stan Thompson.
Stan, where are you from?
Mooresville, but what is? Let me give you my card. What we are involved in that's interesting, and we're involved with you at UNC.
Fortunately, like I said, I realized, actually late last night, I didn't have any business cards with me. But I didn't want to stop back around to get any, so I figured I'd just.
Oh,
and you see them.
And we've got the.
Yeah, hey. Okay. Oh yeah. Fingerprint contact. Yeah. Oh, okay.
Post all the people in the world who are working on this.
Yeah. Have you done any PLM measurements? Yeah, we have measurements. Oh, really? Okay. Oh, nice. What kind of?
Whoever would like a speaker on that, I've spoken on 4 campuses of the UNC.
Okay. Right. To like gallium arsenide?
Google.
So what is hydrel?
Hydrel it's just a just a
Okay, right,
compression
right.
of hydrogen.
I mean, you're naturally going to get a little bit
Okay.
lower just because you're dealing with a lower
And
band
the
gap.
intent
But
of
again,
doing it is for global warming,
the cleanliness and just see sort of,
to diminish the reliance.
you know, whatever chemical
And
behavior
also
is going on.
to
you know, on
diminish
that
the use
surface
of
is good. And
18th
that's
century
like the San Diego guys do all the modeling and stuff. And
overhead
all
wire.
stuff.
So
They
you
do
rely
that.
on them.
Yeah, right. We
Plants.
talk them, so
Okay.
it's screen printed. Yeah.
Yeah, because my producer, Dr. Ivo, he is
This will
also
probably be one of the
very
last
much in the
of
contact.
these
Okay, right.
He's a
operations
All right.
because it saves $10 million a mile.
Okay.
He does a lot of